Hello and welcome everyone to the presentation of the paper, Sparse Activation Map for Interpreting 3D Object Detection. It's a pleasure to introduce my co-workers, Pengfei Li, Meng Xu, and my supervisor, Xiaojun Qi. My name is Qiuxiao Chen, and I will guide you through the presentation. In the presentation, we will talk about related work of the project, proposed method, experiment, conclusion, and future direction. There are two research lines related to our project, DNN-based 3D object detection models and interpretability for DNNs. DNN-based for 3D object detection model is what we want to interpret, and interpretability for DNN is how to interpret. For DNN-based 3D object detection models, we can divide them into two classes roughly, point-based models and volumetric-based models. Point-based models process the raw input points directly, which is time-consuming. The other type, volumetric-based model, work efficiently and are more popular. We will focus on interpreting volumetric-based models. For interpretability for DNNs, plenty of work focus on interpreting 2D images instead of 3D point cloud. As for volumetric-based models, we will introduce two kinds of models. One kind is voxelnet and second, which have similar structures. Second is based on voxelnet and make it more computational efficient. They divide a raw point cloud into equal 3D voxels, and then they apply the voxel feature encoding there to transform a group of points in each of voxel to a feature representation. The other model is PVRCN, the state-of-the-art model at the time when we did this project. The PVRCN model has a voxelized layer, convolutional layers, and the region proposal network, which is also similar to the backbone structure of voxelnet in the high level. With the complex structures and the nonlinearity of the deep neural networks, it would be difficult for us to understand the black boxes. In 3D object detection networks, the input is the raw point clouds, and the output is the 3D bounding box and their classes. Our paper aims to interpret and visualize the efficiency of the middle layers in deep neural networks. To sum up, opening the black box of DNA is a very important task. Therefore, a lot of researchers has been done to obtain the interpretability in DNNs on 2D images. Only recent works will pay attention to 3D, but only interpret a part of the network. However, this interpretation is clearly not enough, especially for safety crucial system, for example, simultaneous driving system. Therefore, we propose a novel method to provide a holistic interpretability for 3D DNNs. Now, I will introduce our proposed method in two parts, the structure overview and the mathematically formulations. Our experiment is conducted on Kitty dataset. Here is the structure overview of our proposed method. Now we only show the last classification convolution layer as a simple example. Given a 3D point cloud containing as input, we does not have we forward propagate the data through the volumetric-based models. Our model does not have to know the exact design of the volumetric-based network, since it may vary in different models. The classification layers are convolutional layers. The weights W of a specific class C are then averaged to obtain the average weight vector, which is then linearly combined with the global feature map A to generate the Sparse activation map, which also calls ZAM. This average pooling prevents the loss of data sparsity and maintain data information, which will be shown in the next slide. In SAM, red represents high activation, which means high possibility possibility to contain an object of specific class C, and the blue represents low activation. Each black rectangle contains a ground truth of cars. One blow-up ground truth is shown here. As for the middle layers in 3D and 2D convolutional layers, the algorithm is similar. More details can be found in our paper. Now we will show the function of our proposed methods as at the classification layer. For comparison, we will go over the conventional equation, which is convolution operation first. Let AM represent feature map of channel M. WMC represents the convolutional kernel that contains the M's channel and the C's class. The prediction score of the C's class is computed by convolutional kernel star feature maps, where star is the conventional convolution operation. The conventional operation cannot work well for interpretation when the input data are sparse, which will be illustrated in the next slide with a toy example. Then we will go over the proposed equation, which is customized average pooling operation. Corresponding to the process of the right picture zoom in from our structure overview, AM, WMC have the same meaning as previous, and WMC IJ represent the convolutional kernel weights, which is coefficients at location IJ. M is the total number of channels of feature maps. N is the total number of pixels in the kernel, and the dot is the dot product. In this equation, we reduce the convolutional kernel to a value, which is the average of the kernel. This value is multiplied with feature map to generate the weighted feature map. A linear combination is then applied to combine all channels of the weighted feature map to yield a sum of channel C, which is annotated as map C. Our proposed equation aims to maintain the data sparsity, which will be also illustrated in the next slide. Here are two toy examples. The feature map in the first line has no neighbors, and the second one has only one neighbor. We can observe with a conventional formula. The result is very dense, while our proposed method can still preserve the sparsity. Here is overall effect on whole maps. The left picture is the output of conventional convolutional operation, and the right picture is the output of customized average pooling operation. In the left images, there is a blurring and a ringing effect, while the right image maintains data sparsity. Therefore, our method can easily locate the high activation along the road, while the existing method cannot. In experiment, we aim to explain three state-of-the-art volumetric-based models, namely second, part A2, and PVRCN. By comparing the average precision, visually interpreting of intermediate layers and the last classification layer. Table shows the performance of the 3D network on cars, pedestrian, and cyclists. We observe that on car and cyclist class, PVRCN has best accuracy. Part A2 performs best on pedestrian class. Let's talk about another example. This feature shows the visualization of three object classes, car, pedestrian, and cyclist in the final sum. The map is generated from the last classification convolutional layer of three volumetric-based models. The ground truth shown in green rectangle includes three cars around the road, and one pedestrian in the lower part, and also one cyclist. Here, extra activation areas of all three models also lead to some false positive detection results. For example, for car, second and part 2 have many extra activation areas along the road and outside the point clouds. here and here. They will get a lot of false positive because of this. By comparison, PVRCN look very clean and only have 3 small wrong activation areas. Only 3. For cyclists, the observation is similar. All these observations based on the activation area in SAM are in line with the detection performance reported in the previous table. To further demonstrate the details of SAM in classification there, we show the blow-up results of second part A2 and the PVRCN within the ground truth bounding box of car, pedestrian, and cyclist. They all perform similar within the ground truth bounding box. In the figure, we will only show the sum of PVRCN to illustrate the effectiveness of intermediate layers. In this example, we slice the point cloud to 5 pieces based on the Z value of the point cloud. Little activation in SAM is captured in first, fourth, and fifth fictions. Since this part does not contain any point on car, the second section C mostly contains points on the road, so the activation is not so clear. The third part of point cloud contains most points of the car. The activation of SAM is very high. Therefore, our tool can be used to locate the activation area in 3D space. In this example, we randomly choose 2 channels from the same intermediate layer to show each neural provides different activation in this SAM. For example, there are a strong activation around the car, shown in the SAM on the left, and there are strong activation around the road region and the car, shown in the right SAM. If we decide to supervise the noise in the final outputs, we can give the second channel a lower weight. To sum up, we think SAM can work well as a performance and analysis tool. To the best of our knowledge, our proposed interpretability model is the first work to provide insight in the middle layers, like 3D and 2D convolutional layers, which can inspire more research to improve the 3D detection structure. Without a need for model architecture change, this visualized result can efficiently compare the subtle differences between each model. The customized average pooling of convolutional layer weight could maintain the sparsity of point clouds. Here are 2 future works for this project. One is using SAM to find potential object, which is unsupervised learning. The other one is find the quantitative measure for the SAM, which is circle the high activation area and calculate accuracy. Thank you, and any question?
Yeah, thank you for the presentation. Are there any questions?
Could you maybe go to slide 9, please?
Okay.
So regarding the SAM map, so we can see that there's high activation just inside the box. Does this mean that the context here for this prediction was not so relevant, or how's your interpretation of this?
It is kind of like try to detect the center of the car, and we have the fixed anchor size. So it doesn't matter if the activation does not fill the whole car.
Okay, and why is it not outside the car? Because I could imagine that there the context plays also a relevant role for the prediction. Or is it maybe a limitation of the approach, how to generate the SAM maps?
I'm sorry, you mean why there is not activation outside the grounding balls?
Right.
I maybe this picture is not so clear since I kind of cut the images to show the best how to the result is from the SAM, but actually the result is kind of like have some other sparse activation around here. So I just choose the best result.
All right, thank you.
More questions?
Maybe another question regarding the evaluation of those activation maps. Could you find a correlation to false positives, or what are in general criteria to evaluate those maps?
You mean here? I kind of, our is only the qualitative evaluation now. We are not, cannot get the exact number to evaluate it. But I think in future, we can kind of like get the high accuracy, high activation and point out the where is the right one is some similar, and we can get our own high activation detection, and then compare with the ground truth, and then we can calculate our own evaluation in the future.
Okay, so this is further work.
Yeah.
Okay, thanks.
Okay, one more question.